Hi, this is Mrs. Cribb, and this is the Chapter 2A Instruction video. One thing that you need to do before we go through this is print these notes out. They're under RenWeb resources, so I'm going to show you that. You go to, this is a parent's web, and if you look at the classes, it doesn't matter which class you look at. There it is, Chem Chapter 2 notes is right here. So you can just pull that up and ta-da, and go ahead and print them out. So if you haven't done that, please stop to do that before you continue. And we're going to move on with this video. We're going to be using the Prezi for Chapter 2. And this Prezi is also under resources, so you can pull it up and watch it yourself or review some of the videos. But this instruction video, we're going to kind of use the Prezi some, and we're going to actually write on the notes themselves when it's needed, that is. So let's go back to the Prezi. Make it full screen, and we're going to get started. So matter, anything that takes up space, that means volume, and has mass. Matter was created by God out of nothing, unlike what Carl Sagan said. From ex nihilo, that means out of nothing. So it has mass, that's the physical stuff that it's made out of. And it has volume, which is the space that it takes up. So like this is 8 ounces of volume, and these all take up different amounts of space. Changes in matter. So first, matter is described based on the properties which are its distinguishing characteristics. So we have physical and chemical properties. Physical properties are things like malleability, which is how you see how you can pull the silly putty into little, you can pull it out into strings, and we would have actually maybe done this in class, but or you can mold it into something else. Malleability has to do with those kind of properties. The ductility is pulling it into kind of strings. You could also do that with silly putty. Physical properties are things that you can use your senses to detect, like color and shape and how much it weighs, volume, the boiling point, melting point, density, how closely packed the particles are, weight, which pulls down in your mass. Is it magnetic? Those are physical properties. Also state of matter, that it's solid, a liquid, or a gas. Something called luster, which is how shiny it is, like this piece of metal, or solubility. That just really means, can it be dissolved in something like sugar and salt? Let me go back to the previous. So physical properties are related to the physical relationships among the particles of matter. How are the particles related to each other? Physical properties are measured without changing the composition. That just means we're not going to rearrange the atoms. They're going to stay into their shapes. And I list some of them. We talked about them in that slide a minute ago. And just some that that silver is the most electrically conductive metal. That's one of its physical properties. It conducts electricity very well. And wood is a very poor conductor of heat. So those are physical properties. They don't change the material. Now we have chemical properties, and they are related to how matter changes in the presence of other matter. Chemical properties are measured by a change in composition. What's it made out of? What's it look like? When a new substance is formed from the old substance. Some examples, like does it rust? How easily does it rust or burn? That's combustion or flammability. Or decompose, fall apart into little pieces of something else. A reaction between gasoline and oxygen is a combustion reaction, and that forms new things. So let's look at this slide. We have methane, CH4, and this is what the molecule looks like. And we have oxygen, O2, and these are two different substances, a compound and a molecule. And when they react together in the presence of heat, they rearrange, and now we have something different on the other side. We have water, H2O, and we have carbon dioxide. So now we've got two completely different compounds over here than we did originally. So that would be a chemical change that happened, and a chemical property would be how easily can it do that? How easily can it change? So chemical properties are combustibility, how easily does it react, or flammability, turn it, burn. Those are all chemical properties. How easily does it do those things? Physical changes are changes that occur in matter without changing the identity, without changing what it is, without changing what it's made out of. Changes in the state of matter, like melting or freezing or condensing or vaporizing, those are all physical changes. If I melt ice cubes into liquid water, it's still water. It's liquid water or solid water. If I turn liquid water back into solid water, that's freezing, still water. If I condense it, like the water comes out of the air and forms on the side of my cold glass of soda, then it's still water. And if I vaporize it, if I turn it from a liquid into a gas, it's still water. Other things that are physical changes are changing the shape, like cutting it up or just breaking it apart. Grinding wheat into flour, it's still made out of the same stuff. Dissolving sugar in water. When you taste sugar water, it's sweet, and so you know the sugar's in there, and it's wet and liquidy, and you can taste the water as well. But both compounds are still in there. So here's just an up-close picture of condensation. We have liquid water forming from water vapor. And then this is just talking about dissolving sugar. This is a sugar molecule surrounded by water. So inside the glass we have water, we have sugar, and they're both still there. They're not changed. The atoms have not rearranged. They haven't come apart and rearranged. Chemical changes are changes that change the identity of the matter. What is it? It changes into something completely new. You start off with one compound and end up with something different. These are not easily reversed. So like rusting, if I rust something, it's very hard to turn it back. If I eat something and it gets digested, I can't reform what I ate. Burning something causes ashes to be made, and you can't reform what I burned. Rotting. And then it says, remember the sugar demo, and that's something I normally would do in class, so I may do that at a later time. Here we have a physical change of just chopping up the wood versus a chemical change. I'm turning it into completely new substance. When I chop up the wood, I just have little smaller pieces of wood. When I burn it, I have a whole new thing. So we're going to watch
will
a couple.
show us
Okay,
that frozen water is
Let me pause it. There we go. I got to rewind this. We're going to watch a couple of videos here, and hopefully this will help explain this even more. Now, I may not watch every video, so if I don't, you're welcome to watch them by pulling up the Prezi at home. But I do want to watch this one.
chemical and physical changes. Say hello to Mark and Molly. Each are enjoying a glass of water. Deciding to save some for later, Molly puts her glass in the refrigerator, and Mark decides to put his in the freezer. A short time later, they go to get their drinks. Molly enjoys her cold liquid water, but something has happened to Mark's water. His has physically changed. Matter can undergo a chemical change or a physical change. A closer look at ice will show us that frozen water is H2O molecules made of hydrogen and oxygen atoms. When the ice cube melts, the molecules stay H2O. They just change from a solid to a liquid. Even when water evaporates, the molecules might be moving a little faster, but they're still water molecules. Another example of a physical change would be bending iron metal. Iron can be made into I-beams or pressed into shapes. Whether the iron is in a beam or in a shape, it still is Fe atoms, just in a different shape. A chemical change occurs when an entire new material is created or the atoms become rearranged. Iron rusting is a chemical change because the iron turns into a new material. The process of rusting can be seen in a chemical formula. Iron plus water plus oxygen yields iron 3 oxide, or rust.
Now look at this for a moment. You see that? You have iron here all by itself as the pure element. We have water and oxygen. The atoms break apart, rearrange, and form iron 3 oxide, which is the rust. That's a brand new thing.
In this chemical equation, we start with iron, but end up with something brand new. Another chemical change happens when you eat sugar. Sugar enters your body as C6H12O6. When you breathe in oxygen gas, a chemical change begins. The sugar is broken down and turned into carbon dioxide and water. The sugar molecule has chemically changed. Another chemical change happens when you drive your car. Gasoline enters your car as octane. Octane is C8H18. In your engine, oxygen is introduced, and the octane changes into carbon dioxide and water. This is a chemical change because octane is no longer a molecule. Something new has been created. You can tell the difference between chemical and physical changes because chemical changes can't easily be undone. But lucky for Mark, a physical change can be undone, and his glass of water is almost back to a liquid. Chemical.
Okay, we're going to watch
Let's start
parts
with
of this
rotting
one,
fruit.
and I'm just going to.
We know a chemical change has occurred, but
Okay, when you know a chemical change has occurred when you have an odor, you see a smell, you smell something, you see a color change happening possibly. Maybe you're forming a gas, it's putting off some heat, or a precipitate, which we're going to talk about forming a precipitate later. But what I'd like you to do now is we're going to look at the different possibilities of change and see if you can categorize them.
but if it's simply a change of state, it's physical. And so let me give you these examples. You may want to pause the video at this point and try to figure out which of these are going to be chemical changes and which of these are going to be physical changes. So let's start with rotting fruit. Rotting fruit, do we have production of gas? Maybe. Do we get a change of color? For sure. Is it easy to go from rotting fruit back to fruit? Not really. And so what would we call that? That would be a chemical change. Let's say we're rusting iron or rusting a metal. What's that going to be? We would call that a chemical change. What's some evidence? I would see a change in color. When you rust things, you're actually going to see a change in heat as well. And it's hard to reverse that, so that'd be a chemical change. Let's say we take a pill of aspirin and we crush it up. Would that be chemical or physical? Well, I don't see change in color or heat or odor, no gas being produced. So that's going to be a physical change. What about burning paper? What are we doing? We're actually combining it with oxygen. It'd be hard to go back to paper again, and so I would call that a chemical change. What about boiling water? We're adding heat to it, but the reaction is not generating heat, and so we would call that a physical change. This is a hard one. What about dissolving sugar in water? Well, when we dissolve the sugar in the water, it's still sugar inside the water. It's simply separated all those sugar molecules, and so we call that a physical change. What about melting butter? That would also be a physical change. It's still butter, we're just changing the form. It's now in a liquid. If we were to burn it, it's combining with oxygen, so we'd call it a chemical. And so what are some chemical changes that you should get used to?
Okay. Now this, I'm going to rewind and maybe listen to just a little bit of it, but this is this guy right here. He has a lot of fun. He makes songs up and sings them, and they're science songs, and I'm all about singing silly science songs because you can remember stuff. So I do have a policy that if you memorize any of the songs on the Prezi, I will give you bonus points, up like 10 bonus points for videos like this, and then if you actually do something really big, we'll talk about what that can be later. So we're going to listen to this for a minute, and then you may decide you want to memorize this to help you learn.
Sometimes it's difficult to come up with the words to describe the differences between a physical property of matter and a chemical property of matter. Physical properties of matter help us to describe and observe matter, and they often involve our senses. The chemical property of a particular substance is that particular substance's potential to change into a new substance, usually when it encounters another substance and it may involve some form of energy. This next song, called the Property Song, will help you distinguish some of the characteristics of both properties of matter. Physical and chemical properties help to tell what matter's all about. All you have to do is know some simple facts that will help you separate the two apart. your senses tell you so. Can you measure the matter in some way? That's physical for sure, oh by the way. Color, odor, size and state and boiling point, or melting point, or gold density. And don't forget there's also solubility, all of these physical properties that be. What you see, what you hear, what you smell, yeah, that's physical, your senses tell you so. Can you measure the matter in some way? That's physical for sure, oh by the way. What chemical properties are different? They help us see if substances will change. When they meet another substance in their way, their atoms may decide to get all rearranged. What you see, what you hear, what you smell, yeah, that's physical, your senses tell you so.
Okay, I'm not going to make you listen to the whole thing, but if you want to earn that 10 points, you can go listen to it on the video and sing it for me, and I will be glad to give you 10 points. Now we're going to move on. We're talking about the classification of matter. This is just the chart. This chart, it's the exact chart that's in your notes. So we're going to go through this. First, we have pure substances. They consist of one type of matter. They cannot be separated into other kinds of matter by physical means. Elements are made out of one type of atom, are represented by symbols. Now, what I'm going to do right here is I'm going to go to the notes so I can write in what these are, and you can fill these into your notes, okay? So down here, so elements made of one type of atom, here we are represented by symbols like hydrogen. Now hydrogen is diatomic, so it's going to be H, and then in the subscript, a little number 2 at the bottom. So please write it like that. We'll talk about these diatomic elements soon. Copper, whose symbol is Cu, and nitrogen. Nitrogen is also diatomic. Okay, with this 2 at the bottom. Compounds are 2 or more elements that are chemically bound together. They hold each other. They're sharing electrons, or they're shifting electrons. And here's some of the compounds: water, carbon dioxide, sugar, which he talked about in one of those videos, table salt. And then mixtures can be separated by physical means into 2 or more pure substances. So mixtures are, you take 2 pure things, you kind of combine, you don't combine them, you just mix them up together, but then I can unmix them. So I like girls and boys. I can put a classroom and I can have some boys and I can have some girls and, you know, another girl over here. I should put a little skirt on her so you know she's a girl, plus she has long hair. So this is a mixture, okay? I have girls and a boy, 2 pure things, and then I mix them up and I could separate them as well. And so mixtures can be separated. There's homogeneous mixture. Homo means the same, so it looks the same all the way through. It has one phase and appearance all the way through. Like Coca-Cola usually looks the same all the way through, maybe except for the bubbles. If you see bubbles in there, that would be a little bit heterogeneous because you have gas in there. Our classroom is going to be heterogeneous because we're going to have girls and guys, and it's probably going to not be perfectly mixed up. Homogeneous examples are sugar water, air, salt water, cola, coffee. Those could be homogeneous. Homogeneous mixtures are also solutions. In fact, a homogeneous mixture is the definition of a solution. And sometimes when I see that, I will take an arrow and point to it in my notes. Like a homogeneous mixture is called a solution. Heterogeneous mixture have regions called phases, and that's just where you can see the separation. I'm going to go back to the Prezi for a moment because I have a few pictures that show you that. Now let's look at this. A compound is a molecule that contains at least 2 different elements, and so pure substances can be elements or compounds. See, elements or compounds. And so a compound has 2 different elements, and then molecules have only one type of element. So that's something that kind of gets people confused, but I'm not going to worry about it too much. We're going to refer to them both throughout the year. A compound is a molecule that contains two different elements. And then a molecule like hydrogen or oxygen or nitrogen are not compounds because it's composed of a single type of element. Okay, there's the mixtures, and it talked about phases. So let's just look at a pure things. This is an element. This is chlorine, also diatomic. See that too? This is sodium metal, and it's easy to cut. One of the physical properties of sodium, it has that luster, that shininess. And then we have compounds, salt. Now if you look at that, there's salt, NaCl. It's made of two different elements. It's a pure substance because all of this is these two things stuck together. And also we have sugar over here. I'm not zooming in too well. There you go. Sugar is a very complicated compound. It has lots of elements stuck together, but it's all, each one of the little grains in there is made out of this compound, all those different atoms. And then I talked about mixtures, and then before I go, this picture, notice how it's beautiful and colored here. But look, this is a homogeneous mixture where they're going to be mixed up evenly. This is a heterogeneous mixture where you see the phases. You have them separated a little bit. They're mixed up, but they're not mixed up perfectly evenly. So there's cream coffee, sort of homogeneous, Coca-Cola, and then the heterogeneous mixture. There's the two phases. Like this is oil and vinegar. They don't mix well, and so you have phases where they're separated out. So you have the oil phase and the vinegar phase. And this is soil. Soil is also a heterogeneous mixture. You have clumps and rocks and things that are mixed in there. They're not evenly dispersed. I think like mashed potatoes.
Much smaller.
Okay, this is a video about pure substances versus mixtures. And I'm not going to play this video for us in this particular Prezi instruction at this point, but I do want you to use this kind of video to help you to separate pure substances and mixtures in your brain. Okay, and that brings us to elements, and I'm going to go back to our notes so I can write. Okay, elements cannot be broken down into simpler substances by ordinary means. That's the key, by ordinary means. Of course, I can break down an element and make an atomic bomb and things, but I'm talking about ordinary means. Monatomic, mono means one. So one atomic, one atom. They're an element whose atoms do not combine with other atoms, and there is one atom in the formula. Neon, helium, argon, and xenon. They all have one atom. And then diatomic. Di means two. So diatomic element is an element whose atoms bond in two atom units. That's when you see them out by themselves. So hydrogen is diatomic. When I just find hydrogen, it's in the form of H2. It has hydrogen and it bonds to hydrogen atoms. And so nitrogen is diatomic, N2, oxygen, O2, fluorine, F2. Notice that it's not FL, it's F2. Chlorine, Cl2, bromine, Br2, and iodine or iodine, I2. You have to memorize these, okay? Now, what I always say in class, and we'll do this a ton, is we go hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So you'd be able to write hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And you have to memorize the diatomic elements. It's going to be important for all kinds of things throughout the year. Polyatomic elements. Now before I do that, I'll go back to the Prezi because I do have a picture. There's some diatomic elements. Hydrogen, oxygen, nitrogen, and chlorine. See how they're bonded together in two atom units. And if they're found on the periodic table, 7 of them, there's 7. 1, 2, 3, 4, 5, 6, and then hydrogen is all by itself. It's usually found way off over here on the left. It's like the super 7. Or the secret 7. 7 diatomic elements. They form this number 7, and the hydrogen's way out to the side. Memorize those. So polyatomic elements. Now see this study stack? We're going to come back to that in a moment. So let's go back to the Notes. Polyatomic elements are elements whose atoms bond in multi-atom units. That means more than two, basically, we're talking about. Like sulfur. Sulfur can exist as S8. That is still a pure element because it just has 8 sulfur atoms stuck together. Oxygen can exist as O3. That's still a pure element. It's called ozone. Element symbols are often the first letter of the name. If there are 2 letters in the symbol, the first letter is capitalized and the second is lowercase. All right, the discoverer of the element gets to name it. So these names must be approved, though, by the International Union of Pure and Applied Chemistry, or IUPAC. So if I discovered an element, I might want to call it Cribium. There we go, Cribium, and then, but I couldn't have it, the symbol could not be Cr because that's chromium. And so I might do Cb, and they would be able to approve it. And I'd have to have that lowercase b because I already have other things like copper that has a C as the beginning, and carbon that has a C. So I'd have to distinguish it by putting that second lowercase letter. So my Cribium element would be Cb. Some examples of some elements and their symbols are aluminum, which is Al, and helium, which is He, and potassium, which is K, and that's weird, but that's because it doesn't come from the English name. Sulfur, carbon, and cobalt. Now, please make sure you fill this all into your notes. Now, this says, see the study stack and learn the periodic symbols. Okay, so the study stack is embedded in your Prezi. So when it's embedded, all you do is click on it, and it'll pull it up. And here's the study stack. And these are all the elements that are in the study stack that you're going to have to know, the name and the symbol. Some of them we're going to learn in order, but some of them we're just going to have to know because we use them a lot. So please make sure you use this study stack. There's all kinds of different things. Matching is one of my favorites. So I'm going to match this up, let's say magnesium, and find the magnesium Mg. Okay. Let's see, arsenic, As, manganese, lead, silver, tin, argon, silicon, fluorine, and titanium. Ta-da, there's a picture. So make sure you use the study stack a lot to memorize these elements. I will let you know when you're going to need to know them for the test, but that's where it is and is available for your usage. Okay, and that brings us to compounds and their formulas, and this is where we're going to have to start actually doing some practice work. So I'm going to go back to my notes, and I don't think I need to stay on the Prezi any longer. Compounds and their formulas. I don't know for sure if this page number is correct. Page 29. So there's a table that you could look at, but I will tell you this, that you don't have to refer to that table. I tried to make sure I updated my notes, so if my notes are not perfect, I apologize. Please let me know. Compounds are made of atoms from 2 or more different elements. Molecules are the smallest individual units. In many compounds, they are made of 2 or more elements chemically bound together. 2 or more elements, but not different ones. And they can be made of the same element or 2 different elements. So you see there's some crossover between these 2 guys. So I'm not going to worry about perfection in that. We're going to just refer to both of those. Formulas represent compounds and tell what type of element and how many atoms. The smaller numbers written at the lower right are called subscripts, and the coefficients are the numbers in front. So let's look at this because it's easier to do this than to really talk about it. In fact, I'm going to make this bigger so that I can write on this a little bit better. So let's look at this first one. The subscript is the 2, the smaller number. The subscript here is the 3 and the 4. And the coefficient, this right here, the coefficient, that's the number 3. Okay? Now this number 3 multiplies everything. This is the compound itself. That's the compound. This 3 says I have 3 of these compounds. This subscript only multiplies everything inside the parentheses. Sort of like in math, I have 2 times x plus y. I'm going to distribute that too. So 2 times x is 2x, and 2 times y is 2y. Or I could have 3 times, oh gosh, that's probably just the best example I can do there. So if I'm going to count the atoms here, I'm going to start off listing them. I have calcium, oxygen, and hydrogen. And then how many calcium atoms are in this compound? Well, in the compound, there's 1 calcium atom. See, the subscript is missing, so that means it's 1. But then I have to multiply everything by the 3, because I have 3 of these compounds and not just 1. So I have 3 calcium atoms then. Now what about oxygen? Well, inside the compound, I have 1 here, 1 times 2, so I have 2, but then I have to multiply that by the 3, the coefficient of the 3. So I actually have 6 atoms of oxygen. All right, now what about hydrogen? Same thing. There's only 1 hydrogen inside the compound, but I have to multiply it by the 2 because of the subscript, so that's 2, and then I have to multiply it by the 3 because of the coefficient, so that's 6 atoms of hydrogen. All right, so that's the number of atoms for the calcium hydroxide. This is calcium hydroxide. Now what about over here? Well, there's no coefficient, so when there's no coefficient, you assume that it's a 1. So this one's actually very easy. We have sodium, and that subscript of 3 tells me 3 atoms. Okay, we have phosphorus. Now notice this subscript, it only pertains to the 4, or to the oxygen. See, it has to have parentheses over here, like this one. The parentheses makes that 2 pertain to both the hydrogen and the oxygen. There's no parentheses over here, no parentheses. So the phosphorus, there's only 1 atom. 1 atom. But for oxygen, there are 4 atoms. Okay, so now, let's go to the other side. This is the same exact molecule or compound because it has more than 1 atom and it has different types as the one before. See, this compound is identical to this compound. But here I only had 1 of them. Now I'm going to have a different coefficient right here, the 2. So now I have, instead of having 1 of them, I have 2 of them. So I'm going to count the total number of atoms present. We have sodium. I start off with the 3, the subscript, and I've got to multiply it by the 2. So that's going to give me 6 sodium atoms. And then I'm going to have phosphorus. I start off with that 1, but I have to multiply it by the 2. So I have 2 phosphorus atoms. So these are atoms. And then I have oxygen. I start off with that 4 from the subscript, but I have to multiply it by the 2, the coefficient. So I have 8 oxygen atoms. So that's how many atoms I have of each type. Now I could also ask you how many total atoms. So over here, the total atoms would be adding all these guys together. So if I have the total atoms, I have 3 plus 1 plus 4. So that's 7, 8. 8 total. If I want the total atoms over here, I have 6 plus 2 is 8 plus 8 more, 16 total. That makes sense because I took a coefficient of 2, meaning I multiplied that compound twice. I had 8 over here, so 2 times 8 would have been 16 over here. So please be careful. Now what I'd like you to do is you are going to answer the ones for, the seat work. Let me make this smaller. So I'm going to ask you to answer how many atoms of each of these in the question on the Ed puzzle, okay? And that will be the end of the notes for Chapter 2A. So once you finish answering these questions, we'll be done with that, and I'll create a different video for the Chapter 2B on energy and matter.